Okay, so we're going to be doing lead code 153, find minimum in rotated sorted array. So suppose an array of length n sorted in ascending order, right, is rotated between 1 and n times. For example, the array num 0, 1, 2, 4, 5, 6 might become 4, 5, 6, 7 if it's rotated 4 times. So it's rotated 4 times because this gets taken this side, and then this gets taken. Let me show you what the rotation looks like. Right. So they've given us. We're going to first put these. So they've given us the array called nums, which is 0, 1, 2, 4, 5, 6, and 7. And they're saying rotated 4 times. So what that means, the first time, second, third, and fourth. Right? So the first time it becomes, this comes here. So it becomes 7, 0, 1, 2, 4, 5, 6. Right? The second time this comes here. So it becomes 6, 7, 0, 1, 2, 4, 5. Third time this comes here. It becomes 5, 6, 7, 0, 1, 2, 4. And then the fourth and final time, this comes here, becomes 4, 5, 6, 7, 0, 1, 2. Right? So let's continue. Let's rotate it. So this had a length of 8, right? 1, 2, 3, 4, 5, 6, 7. It had a length of 7. Let's rotate it 7 times, right? So we're currently at 4. We're going to go to 5. This is gonna come here, so fifth time will be. The fifth time will be 2, 4, 5, 6, 7, 0, 1. The sixth time will be, this comes here, 1, 2, 4, 5, 6, 7, 0, right? And the seventh time will be, this comes back here, so it becomes 0, 1, 2, 4, 5, 6, 7, right? So notice that when you rotate it to a number of its length, you come back to the original sorted array, right? The other thing is that there's no way you can rotate it and make it in decreasing order, right? So that's why I wanted to do this, right? So, oh crap, hold on, delete that. Okay, we're gonna delete this as well. Delete all these. Okay, so I just wanted to show you that, which is very important to understanding this question, right? So, notice that rotating an array one time results. I've illustrated that. So you're given the sorted array nums of unique elements, return the minimum element of this array. So you're given a sorted rotated array. We don't know how many times it was rotated. We don't know if it was rotated back into its sorted position, but they want us to find the minimum element, right? So we're going to use this. So in order to find the minimum element of a rotated sorted array, it will either be at this position if it was rotated back, if it was rotated number of length of the array, it will rotate back to its original position, so the minimum element will be at index 0, right? Otherwise, the minimum element will be at this position. And what is this position? This position is a position where array at position, no, the minimum element will actually be at this position. Sorry. The minimum element will be at array at position, right? Then we identify this position. It will be the position where, I think it's much easier to find out the position before the minimum element if there's a rotation that leads to an imbalance. And that position is this position, the one before the minimum element. And array at this position is greater than array at that position plus 1, right? Because notice these are all going to be increasing and these are all going to be increasing, meaning that the value at the ith position is less than the value at I plus 1, right? Except for this condition. So if we're to do it in linear time, all we're going to do is we're going to iterate from this side until we find an array at I where the value here is greater than array at I plus 1, right? And if we do not find such a location, it means our array either was not rotated or was rotated back into its sorted position where the minimum element is at this position, right? So let's do the linear time solution, but which is not the solution that's required, right? So for the linear time solution, we iterate until we find array at I is greater than array at I plus 1. So for I in nums in range, it will be length of nums, so length of nums, right? If nums at I, actually we'd want to have space for the last index, so we'll iterate until the second last position, right? Let me show you what I mean. We'll iterate from index 0 till this position, right? Because we want to be able to check for array here greater than array here, right? So let's do that in our code. So it will be from array, this will be from 0 till length of nums minus 1. So if nums at I is greater than nums at I plus 1, then we have found the minimum element for the whole array. And that will be at index I plus 1. So we return nums at I plus 1. Right? If we didn't find it using the condition, then it means our array was either not rotated, so it's in sorted order, or it was rotated back to its original sorted form, i.e., it was rotated length of array times. So we simply return the value at index 0 as its minimum. So we return nums at index 0. And voila, this works. But they want us to do it. You must write the algorithm in O of log n time, right? So how do we find the minimum element in log n time? Well, it's actually not tricky. You just have to notice a certain thing about this array. Since they want it in log n time, it means one thing, binary search, right? But how are we going to do the binary search? What condition are we going to use to exclude? We know that our I is at this position, our j is at this position, right? We're going to imagine that it was not sorted length of array times, and it was also maybe not sorted 0 times. So meaning that it's now in a distorted form, right? So what we're trying to find is we want to return this, right? And luckily, because of this distortion, right? If we find the right function, the right mathematical function or equation, it means that after exhaustive binary search, right? We're going to be using exhaustive binary search. After exhaustive binary search, our I will be at this location and our j will be at this location, right? Meaning that if we want to return this minimum number, we'll be returning array at I or array at j plus 1, right? So the mathematical function, the one thing you have to note about this array is that it's not even a mathematics, it's an observation, right? All these, let me write them in green. All these are in ascending order, right? But on top of it, there are all these, do it like this. All these are larger than all these, right? All these are larger than all these, right? Than all these. Right? So how do we identify that we are in this section? And how do we identify that we are in this section? So since our focus should be on our I. So since our I starts out at this position, right? When we calculate the mid, we want our mid to be, we want to determine if it's still in this section, then we want our I to jump forward. And the condition is that, the condition you have to use is if array at the mid is greater than array at last position. And the answer is that 4 is greater than this. 5 is greater than this. 6 is greater than this last position. 7 is greater. 8 is greater. So all the ones in the distorted section that were rotated are greater than the last element, right? As long as the array is distorted. So what will happen is, when we calculate our mid, say for here, our first mid will be 0 plus 7 divided by 2. Our mid will be here, right? So then we check, is this greater than, is 7 greater than 3, which is at our last node? Yes, it is. So we bring our I past the mid, it comes here to 4, right? Then we say, we calculate our mid again. 4 plus 7 gives us 11. 11 divided by 2 will give us our mid as here, right? And then we ask ourselves, is the value at the mid greater than, is the value at the mid greater than the last one? Then it's not. So we push our I past the mid. So our J, actually, our J comes here, right? But remember, our condition terminates when I goes past J. So now our mid is, so now we're going to calculate a new mid, right? Our I is 4, our J is 4. 4 plus 4 gives us 8 divided by 2 will give us 4. So again, we ask ourselves, so now our mid is here, right? We ask ourselves, is 8 greater than 3? Yes, it is. Our I moves, and why 3? Because it's the last one. Our I moves, and now our J is at this position, right? Our J is less than our I, so we terminate, and we return the array at I is our minimum element, right? The other thing is, if our array had been kept in its sorted position, or it had been rotated length of array times, then what will happen is our I is here, our J is here. We'll never satisfy this condition, and we'll simply be moving our J all the time. So whenever we calculate our mid, our J will move, say, to the middle. We come back, we calculate our mid will move to 2. We calculate our mid for 2 and whatever, our J will move here. We calculate our mid, our J will move here, and it will become -1. So we'll return I. So that's how we solve this question, using this as our exclusion principle, our exclusion equation. So let's write it out, right? Let's write it out. Okay, so time for the log n solution, right? So we initialize our pointers. Our I will be at 0, our J will be at length of nums -1. So while I is less than or equal to J, we calculate a mid, which will be mid is equal to I plus J divided by 2. And then we check for if we are in the distorted portion. How do we check for that? We say if array at mid is greater than array at the last position, right? Then we move our I forward, since we want it in the non-distorted portion, i.e. the smallest portion. So our I is equal to mid plus 1. Else, this means our array at mid is actually greater than our array at the last position. So we move our j backwards until it's in the distorted portion. Distorted portion, i.e. the larger values. So our j is equal to mid minus 1. And then when we return, our I will be at the smallest value. So we simply return array at I. Right? And the beauty to this is that, as I showed you, if the array was not sorted, so if the array, was still in sorted order, our I wouldn't have moved. Right? So let's run this and see. Array at mid greater than, oh, sorry, it's supposed to be nums. Sorry about that. Yeah. So this works. If you want, just for the sake of it, I'm going to actually, and you can trace it out yourself. So yeah, this is the solution. It's log n and it takes O1 time. So after you do this, you'll be able to do the question search in sorted array. Right? Very important that you do this. Okay, thank you and bye.